In this video I'm going to look at optical isomerism. So I've got this model of proton 2-ol here, and what I'm going to do is I'm going to position it on the board, and then I'm going to hold a mirror and we're going to have a look at the reflection in the mirror. So that is what we would call the mirror image of the molecule. You can see I've lost the mirror now, and I've actually got a physical model of the mirror image. And what we're going to do is we're going to ask ourselves, are they the same as each other or are they different? So these two molecules are actually exactly the same as each other. There's no difference between them, and we can tell that because we can superimpose them. We can put one on top of the other, and every single bond, every group is in exactly the same position in space. So they are not isomers, they are identical molecules. I'm going to do exactly the same now with this molecule. All I've done is replaced one of the methyl groups with a green atom, which generally represents a halogen, but in this case it's just representing a different group. And there you can see is the reflection, the mirror image. And again, I'm going to make that mirror image model and ask the same question, are they the same or different? So there it is, there's the mirror image. And let's do the same as before. So we want to try and superimpose one on top of the other. And hopefully you'll be able to see that these are now actually different. What we can't do is put one on top of the other and get all of the bonds, the groups on these bonds, to be all pointing in the same direction. And so you can see this white, this hydrogen, is pointing in this direction on this molecule, whereas this one here, the green atom, is pointing in that direction. And so because these two molecules, these mirror image molecules, are non-superimposable, they are therefore different molecules. If we just think about this green atom as being a chlorine, so the structural formula for this right hand one would be CH3, CH, Cl, OH. Now if we look at the one on the left hand side, this one here, CH3, CH, Cl, OH. So they've got the same structural formula. So because their structural formulae are the same, but the arrangements of the atoms are different in space, because we have the green and the white not matching up together, we call these stereoisomers. So this is another type of stereoisomerism, and it's known as optical isomerism. On the right hand side there, I've made the proton 2-ol molecule back up there, and we're just going to quickly explain, well, what is it about this molecule here that means it can show this type of isomerism, whereas this one couldn't. And it's all about this carbon here. So what we've got in this molecule is we've got 4 different groups attached to this carbon. We've got the OH group, we've got the halogen, we've got a hydrogen, and we've got a CH3 group. So 4 different groups. On the equivalent carbon on proton 2-ol, we've got an OH, an H, so we've got 2 groups different so far, but we've got 2 CH3 groups. We've got 2 identical groups, so this has only got 3 different groups attached to this carbon, and this one's got 4. When you have 4 different groups attached to the same carbon, it shows optical isomerism. Carbon atoms that have this feature are known as chiral centers, and that comes from a Greek word for hand, and the link this type of isomerism has with hands is the fact that your hands are also in effect mirror images of each other, and you can't superimpose them one on top of the other, because if you try, your thumb and your little finger are pointing in opposite directions. Typical questions then in exams would be, you may be supplied with a structural formula like this, and the first thing is you might be asked to identify the chiral centre. And so you're looking for the carbon atom with the 4 different groups attached. So the first thing I would recommend is you just draw a quick sketch of the displayed formula, which makes the chiral centre a lot more obvious. So it's this one here, which may be not so obvious in this structural formula. And then once you've got that, you would then probably be asked to draw the optical isomers. So you can see I've drawn the left hand one up first, deliberately not put one in there yet because I want you to watch me draw it. So we've got our chiral centre in the middle, and we've basically drawn our tetrahedral arrangement around there. So I'll just do the same but I'm not going to add any groups yet. So this is what I call an empty tetrahedron. And so what we're going to do is we're going to mirror this on this side. This dotted line, by the way, represents the mirror. And so we've got an OH group up there. And just be careful with your connectivity. The oxygen is bonded to the carbon, so make sure that's evident. The hydrogen is there. The chlorine would be there, and that methyl group would be there. And you can see I've rearranged the order of the groups on the chiral centre, and I just want to show you that it doesn't matter which way you draw these, as long as your mirror is the mirror image of your original molecule. So this would be CH3, so we've got an OH here now, we've got a Cl there, and we've got the H there. And a very important word you can see written up on the bottom, these optical isomers are known as enantiomers. We'll just finish off with this summary board. So a chiral centre is a carbon atom with 4 different atoms or groups attached. Molecules with a chiral centre show optical isomerism. Optical isomers are non-superimposable mirror images of each other. Optical isomerism is a form of stereoisomerism, so they have the same structural formula but different arrangements of the atoms or groups in space. The optical isomers are referred to as enantiomers. If you've got one chiral centre in the molecule, you would end up with 2 optical isomers possible. What I didn't mention in the video, if you have 2 chiral centres, you get 4 isomers, 4 optical isomers. So for every chiral centre there are 2 possible structures.